this class, we'll learn the topic functions from the basics level. First of all, a function is basically a relation from a set to another set. Again, what is a relation? Like this we proceed. We are supposed to start from the fundamentals. Well, let A, B be two non-empty sets. Two non-empty sets. As an example, let A is equal to 1, 2, 3 and B is equal to x, y, z. From the earlier algebra, everybody knows what A cross B is. It is the Cartesian product of A and B, which is supposed to contain ordered pairs of the form 1x, 1y, 1z, 2x, 2y, 2z, 3x, 3y and 3z. A has 3 elements, B has 3 elements, then A cross B has 9 elements. Just like this, if A has m elements, B has n elements, automatically A cross B has mn elements. Why? Because by forming A cross B, it is just nothing but to form all possible ordered pairs in which the first entry belongs to the first set and the second entry belongs to the second set. These two are of course called components also or coordinates also. This is the matter about A cross B. Now, let me grasp a subset of A cross B. Look here, 1, x, 1, y, 2, z, 3, y. Stop there. This A cross B contains 9 elements, whereas this subset has just 4 elements only. What do you say about this set? Is it a subset of A cross B or not? Yes, of course. This is a subset of A cross B. And this is the background to define the word relation. Any such subset of A cross B is termed as a relation from A to B. And we generally use the letters small f, small g, small h like that to represent relations. So, what is the relation from A to B? F is a relation from A to B if and only if F is a subset of A cross B. F is a subset of A cross B. This is a famous notation which must be read as F from A to B. Now and then some students used to say F maps A to B. That is a wrong pronunciation. You have to read this as F from A to B. Basically, it is a relation from A to B. Well, with this understanding, what can you conclude? Any subset of A cross B is called a relation from A to B. Here in this example, what is the relation we are considering? This is the relation. This has been expressed in terms of ordered pairs. There is another way also to express the same relation pictorially also. How? Which is very, very familiar to you. One is related to x. One is related to y also. 2 is related to z. 3 is related to y. We have to speak like that. This is a relation from A to B. By considering such relations and by putting forth certain conditions on such a relation, we are ready to define a function. So to define a function, basically we must have a relation between two sets. So for that we should have two sets, say A and B. Well, this is a relation. Well, there is a standard question also here. A has, say, 1, 2, 3, 4 elements, and B has just 3 elements, say X, Y, Z. The standard question here is, how many relations can be had from A to B? How many relations can be had from A to B? The answer is, of course, 2 to the power of 12. What is the concept behind it? Suppose A has m elements, B has n elements. Well, what is A cross B? How many elements are there in A cross B? Mn elements. By the by, what are we discussing about? We are discussing about number of relations. What is a relation? Every subset of A cross B is a relation. How many relations are there? What does that question mean? How many subsets of A cross B are possible? It's very simple. A cross B is a set with mn elements. So, how many subsets are possible to be obtained there? 2 power mn. Therefore, number of relations from A to B is, of course, 2 to the power of mn. M is the number of elements present in A, n is the number of elements present in B. Totally, the number of such relations from A to B is 2 to the power of mn. Well, our actual purpose is to discuss with a function. But functions are originated from relations. That is why we have noticed the actual definition of a relation. Now, let us turn our head towards functions. Observe this diagram. Call this set A, this set B. Just like in the previous pictorial explanation, we can easily say that this is, of course, a relation from A to B. 1 is related to A, 2 is related to B, 3 is related to C, and 4 is related to D. Well, in this relation, we observe two important aspects. Number 1, every element is related to some other element there. So, no element is kept empty here. Second point is, no one particular element is related to two things there. Those are the two special items. If these two conditions are satisfied, such a relation is said to be a function. As and when we see and we agree with the diagram that f is a function, then entire language changes. If this is a function, you say that 1 is mapped to A, 2 is mapped to A, 3 is mapped to C, 4 is mapped to D. Another style, image of 1 is A, image of 2 is A, image of 3 is C, image of 4 is D. Do you want to speak from that direction? You can. How? Pre-image of A is 1. Another pre-image of A is 2. B, of course, it doesn't possess any pre-image here. We don't bother about it. C, pre-image of C is 3. Pre-image of D is 4. And we now read that f from A to B is a function. After believing that it is a function, there is no sin in speaking that f maps A to B. The word maps itself says that it is a function. F maps A to B is a function. Well, now let us try to express this idea in terms of theoretical words. Good. Not in the case of an example. Let A, B be two non-empty sets. A, B. As there is one more thing here to discuss, we write 1 is mapped to A, 2 is mapped to A, 3 is mapped to C, 4 is mapped to D. That can be expressed again in another way. F of 1 is equal to A, F of 2 is equal to A, F of 3 is equal to C, and F of 4 is equal to D. So to every element here, we have an image here. Suppose X is here. What do you call the image of X? F of X. What is the image of 1? F of 1. What is the image of 2? F of 2. Image of 3? F of C. Image of 4? F of 4. That is of course D. Suppose if this arrow is not present here, what can you understand? This 4 has no image at all under this relation. In such a case, it is not a function. So, to call a particular relation a function, the very first rule that must be satisfied is every element of this set should have an image. How to write that? Let A, comma B be two non-empty sets. Non-empty sets. A relation F from A to B is called a function, if number 1, the first rule to be satisfied is to each A belongs to A, there is B belongs to B such that F of A is equal to B. In words, it can be expressed in this way also. Every element of capital A has an image in capital B. Of course, the image of small a is small b, and the image is denoted by the symbol F of A. Well, the second rule. Look here. How many images are here? Only one. What is that? A. How many images are here? Only one. What is that? A. How many? Only one. C. How many? Oh, you put an arrow like this. How many images are there? Only one. So, image of every element is present, of course, uniquely present. If I put an arrow like this also, then it is not a function. The second rule says that no element in the set A is supposed to have more than one image. No element in the set A is supposed to have more than one image. So this lengthier sentence can be shortened like this. Every element of capital A has a unique image in B. Okay? Every element in A has a unique image in B. If these two rules have been satisfied, then that relation is termed as a function. Well, in explaining these conditions, we have used capital A and capital B only. Hereafter, we name them in a different way. Capital A is of course called domain of the function. The domain of the function. The domain is the place in which in f of x, in f of A takes all these values. The place or the house in which the element A is present is the domain. And the set A, B, C, D, let me rub this off. Why? Because if this is present, this is not a function. Look here. A is domain of the function. B is codomain of the function. What is that? Codomain of the function. Well, ACD, the set ACD is called range of the function. how far these elements range in the set. Where do they go? These two go to A. This 3 goes to C. This 4 goes to D. Here is a waste element in the codomain that is not working as the image of no other element here. We are not interested in it. That is a useless element. That is termed as isolated element of the codomain. It belongs to the codomain but does not belong to the range. So, what is this is the definition of a function, which is of course available in every textbook and in every mind of a student. Well, let us now understand the terminology regarding this definition. We turn our head towards learning the terminology of a function. Let us make use of this diagram. Here, A. What is A? Domain of the function. Domain of f. B. Codomain of f. Codomain of f. And f of A. What is f of A? What is f of 1? Small a. What is f of 2? A. What is f of 3? C. F of 4. F of A is just nothing but the set of all images of the elements of A. F of 1 means image of 1. F of 2 means image of 2. F of A means set of the images of all the elements in capital A. What is that? A, C, D. This is termed as a range of F. What is that? Range of F. Well, let us recall the standard symbols to represent the same. DF, D of F, domain of F. These 3 symbols can be used. Some others used FD also. What do you mean by FD? Domain of F. Right? Similarly, RF, range of F. F of A, range of F. Range means very rare others use this symbol FR to denote range of F. Familiar symbols are these: DF, DF. Some others, R of F is also used by some others. These are the symbols. What do you mean by F of capital A? The set of all images of elements of capital A under F. You gather images for all the elements. That is nothing but the range. Well, in this codomain, there is a particular element B which belongs to the codomain but not an element of the range. Such elements are called isolated elements of the codomain. We have no interest at all to discuss with them. We are interested in dealing with the elements which are present in the range only. Moreover, if you observe the elements of the range, this works as image for one element. This works as image for one element. This works as image for 2 elements. So, every element of the range works as the image for at least one element of the domain. This is about domain, range, codomain, etc. Well, we are just at the footsteps of the chapter functions. With this simple knowledge, we will be able to answer some questions also simply on the basis of definition of a function. What are such questions? Let us see. The very first, very simple questions. Which of the following diagrams represent a function? He is asking. Which of the following diagrams represents a function? That is the question. Look at this diagram. 2 rules are violated here. What is the first rule? to define a function. Every element of the domain must have an image. Does this 3 have an image? No. So it is not a function. Second rule is also violated. This 2 has 2 images at a time. Can one particular person reach 2 different places at a time? Not possible. That is why such a relation is not a function. Like this. What do you say about this? Image is there, image is there, image is there. No element is kept vacant here. No element has 2 images. It is a function. Why do you say that it is not a function? Here, second rule is okay, but the first rule is not defined. That is, 3 has no image at all. For that reason, it is not a function. Of course, such questions you can observe from earlier classes itself. This is the first variety of the question. Well, the second variety. A is equal to 1, 2, 3. B is equal to A, B, C. Which of the following relations, which of the following is a function from A to B? First option, f is equal to 1a, 2b, 2c, 3a. Second one, f is equal to 1a, 2b, 3c, 1c. Third one, f is equal to 1a, 2b, 3b. Fourth, none. You can easily trace the answer. Here the function has been given not in the terms of a figure, but in the terms of a set of ordered pairs. Why? Because basically a function is just nothing but a relation, and a relation can be expressed in terms of ordered pairs also. Well, if you look at these ordered pairs, you can easily trace an actual function. 1 has an image A, 2 has 2 images. Image of 2 is B, image of 2 is C. So it is not a function. Therefore, the first coordinate must not be repeated. We have noticed. Come on. 1, 2, 3, 1. 1 is repeated, not a function. 1, 2, 3. No repetition in the first coordinate. Hence, it is a function. It is a function. Well, this is the second model of identifying a function. Let us now observe the third model. Which of the following graphs corresponds to a function? The first graph, second graph, third graph, fourth graph. Justly looking at those diagrams for the first time, a general student might be confused. Oh, this is an ellipse, we know it. This is a parabola, we know it. So that is a function, this is a function. We did not come across such thing. It is not a function. Okay, tick it. This is a function, this is a function. This is also a function because it is a graph of a sin x. This is also a function. Like that he thinks. No, this is the only function here among all these. Why? Because how to make the judgment, how to decide. Look here, if a graph like this is given, how to take the decision? If you draw a vertical line, that is a line parallel to y-axis, then it must cut at most at one point. It must cut the curve at most one point. At most means if you draw a line like this does not cut at all. If you draw a line parallel to axis like this, it cuts. How many places it does cut? 1, 2, 3, 4, 5. No, it is not a function. What is the reason? Suppose this value of x is a. What is f of a? This or this or this or this. For one element a, how many f of a's will occur here? That is why this is not a function. Just like that. Even though it is a known figure, well-known figure, ellipse, even this is not a function, because if you draw a line parallel to y-axis, it cuts the curve at two different points. It's not a function. Similar is the fate with this. It is also not a function, whereas that is a function. Draw a vertical line anywhere you want, anywhere you want. It cuts the curve at most one point only, exactly at one point only it does cut. That is why this is the only graph which corresponds to a function, and everybody knows that this is the graph of f of x equal to sin x. Of course, I have not plotted the points of the points where the f of x equal to sin x cuts x-axis, but simply by looking at that, we will be able to recall the nature of sin x, and this is the graph of f of x equal to sin x. This is a function. Well, justly using the basics of the definition of a function, we are able to look at three models of problems regarding the definition of a function. Let us now move in an advance. One more simple question based on the definition of a function itself. If a comma b are non-empty finite sets, then the number of functions that can be defined from A to B is one of the familiar answers. It is of course n of b to the power n of a. By n of b we mean the number of elements in B, cardinality of B. Similarly, n of a is also like that. So let us have an example of this formula, rather format. If a is equal to 1, 2, 3 and b is equal to p, q, how many functions are possible to be defined? N of b is 2, n of a is 3. So correct answer is 2 power 3. That is how many functions you can have. At most 8 functions you can have. How many functions you can have? At most 8 functions you can have. This is a beautiful point to be noted. Well, let us discuss with some types of functions. Out of them, the very first function to be noted is identity function. What is an identity function? Identity function. Suppose a set A is there. It wants to identify itself in view of this function. Image of A is A, image of B is B, image of C is C, image of D is D. It is just nothing but the mirror image. If the set stands before a mirror, image of A occurs as A itself, image of B occurs as B itself, image of C is C, image of D is D. As a mirror image function, this is termed as the identity function, and it is denoted by IA. What is the specialty here? Domain, codomain, range, everything. A same set, A to A. That is why we represent this identity function with the symbol IA. What do you mean by IA? Identity function defined on A. That is I from A to A. It has been defined. This is the identity function on A. Similarly, if you write say IB, what do you mean by that? It is the identity function defined on the non-empty set B. What is the basic and characteristic nature of the identity function? I of A, I have B, I have C, I have D, I have X is X for all X belongs to A. For all X belongs to A. Good. How many identity functions are possible to be defined? Foolish question. How many identities will be there for a particular person? There is only one identity, isn't it? Therefore, there is one and only one identity function on a particular set A. It is denoted by IA or simply I. Good. Second one. Constant function. The very name itself indicates some constant nature is being observed somewhere else in the function. What is that nature? Where does it lie? Let us observe. You consider the set 1, 2, 3, 4, A, B, C, D, E, like that. You observe all the elements have been mapped onto A only. B has no preimage, C has no preimage, D has no preimage, E has no preimage, and every element has a fixed image, constant image. That is why this is called a constant function. So, if a constant function is before you, what is the constant there? Image of every element is constant. Image of every element, it does not change. Image of 1 is A, image of 2 is A, image of 3 is A, image of 4 is A. Therefore, f from A to B, if at all it is a function, then f of x is equal to B for some fixed element of B. For some fixed element of B. Of course, in the diagram it is A, f of x is B. For every x, for all x belongs to A. This is of course called a constant function. It is of course called a constant function. What are the special things that you can observe in the case of a constant function? Suppose this is a constant function. What is the range of f here? Come on. How many elements are there in the range? Just one element. What is that? Singleton A. So, this is the characteristic feature of a constant function. How many elements will be there in the range of a constant function? Only one element. Only one element. Next one. In our usual practice, we generally come across functions of this form. F of x is equal to 5, I say, suppose. What does this mean? F of 1 is 5, f of 2 is 5, f of 3 is 5, f of 4 is 5, f of every element of the domain is again 5. So, there is a constant function. We come across certain functions in our usual practice also. This is one of the best examples of a constant function. And the next function that we may have to discuss with is 1 function or an injection. Observe this function. 1, 2, 3. A, B, C, D, E. How many elements are there in the domain? 3. How many elements are there in the range? 3. 1 goes to A, 2 goes to B, 3 goes to C. No element here is mapped to 2 elements. Of course, it's a function. No 2 elements have the same image, isn't it? So, in order to express this idea in words, distinct elements of the domain are mapped to distinct elements of the codomain. Then only that function is called a 1 function or an injection. If A and B are finite, then n of a is equal to n of f of a. N of a is equal to n of f of a. Of course, this is valid when and only when a and b are finite. For finite sets, we write this sentence: n of a is equal to n of b. N of b. Well, this is a beautiful function which can be seen in our daily life. Suppose this is the balcony of a cinema theater. There are 1, 2, 3, 4, 5, 6 seats only, and on that particular show only 4 people purchased the ticket to view that cinema in that theater. Well, this person sits in this chair, this person sits in the chair, this person may sit in the chair, this person may sit in the chair. Even though the seats are empty, can one man sit in 2 chairs? Foolish. Not possible. 1 to 1. One element to possess one image. That is why this function is termed as 1-1 function. What do you mean by 1-1? 1 to 1. Either in this direction or in this direction. What I mean to say is, element has one image. This element has one pre-image. This element has only one pre-image. This element, let it be like that. It has no pre-image. I don't bother about it. Look here. This has one pre-image. This has one pre-image. One image, one pre-image. So in this direction and that direction also 1 to 1. That's all. That is why it is a 1-1 function. Or injection. This has been injected here. These are 4 in number. 4 seats are enough. If you speak of that case in the view of an example, like that we speak of that. That is why such a function is called a 1-1 function. Well, in calculations, there is a particular procedure to test whether a function is 1-1 or not. If f of a is equal to f of b is considered, and if you are able to show that a is equal to b, then you notice that it is a 1-1 function. Images are same means element must be same. If the elements are different, then images must also be different. Therefore, this is the right procedure to check, to test whether a given function is 1-1 or not. Another procedure also is there. What is that? If you take 2 elements, distinct elements A and B, then their images must also be different. Both the types of procedure are suggestible. You can proceed in this way. Of course, this is according to the exact definition, and this is a simplified procedure. F of a is equal to f of b implies a is equal to b. If you are able to show, then it is a 1-1 function. If you are able to show this, then it is a 1-1 function. Both are meant in the same way. Yes, this is the case of a 1-1 function. Well done. What are the things you can observe? N of a is equal to n of f of a. N of f of a, provided a and b are finite. One more thing, if a and b are finite, n of a must be less than or equal to n of b. In order to define a 1-1 function from a to b, you must have n of a is less than or equal to n of b. Why? Because you observe this example. 1, 2, 3, 4, 5. X, Y, Z. Come on, please define a 1-1 function from this to that set. Is it possible? Let us try. 1 to X, 2 to Y, 3 to Z, 4. 4. How can you fix? If you put an arrow like this, then these 2 elements have a common image. These elements are distinct, but images are same. It is not a 1-1 function. So it is a sin. If you leave it like that itself, then it would not be a function at all. Why? Because these 2 are not having the images. These situations may arise if you take n of a greater than n of b. That is why in order to define a 1-1 function, you must have n of a less than or equal to n of b. This is the case of a 1-1 function. Well, let us note down some famous 1-1 functions. Any linear polynomial is 1-1, f of x equal to x plus b. Then what do you say about a quadratic polynomial? It need not be a 1-1. Need not be 1-1 I'm not saying that it is definitely not 1-1. Consider an example, f of x is equal to x square plus 1. Clearly f of 2 is equal to 5. The same f of 2 is f of minus 2 also. Two elements have the same image. Not 1-1. Not 1-1. Of course, if you restrict the domain to set of natural numbers or set of positive numbers only, then it can be termed as a 1-1 function. So in general, it not be 1-1. If you make simple corrections to the domain and range or the codomain, it can be made 1-1. Basically, it need not be 1-1. If you consider the entire set of real numbers as the domain, it need not be 1-1. Well, absolutely, damn surely 1-1 it is. F of x equal to ax plus b. Next one. F from closed interval minus pi by 2 to plus pi by 2 to are defined by f of x is equal to sin x. In this case, it is 1-1. In this case only it is 1-1. If you define f from R to R as f of x equal to sin x, it is need not be 1-1. Need not be. No, it is not 1-1. It is not 1-1. What is f of pi by 6? Sin pi by 6. Half. What is f of sin 150 degrees? Half. So, two elements are having the same image. It is not 1-1. But here in this case, we have restricted the function to have this particular domain. Here it is 1-1. Here it is not 1-1. In a similar fashion, you can be in a position to observe the nature of all the trigonometric functions and their inverse functions also, to examine in what case they can be 1-1. Yes, that is a different aspect. We shall discuss with that while solving some problems. The next function before us is onto function or a surjection. We have noticed the definition of a 1-1 function. We have learnt it. We could have seen so many examples for that also. It is now our turn to look towards an onto function. What is meant by an onto function? Let us see. You tell me whether this is a function or not. No doubt, surely it is a function. Only one image, only one image, only one image, only one image. It is a function. Is it 1-1? Of course, not 1-1. Two elements have the same image. But here, the special thing that you can observe is, what is the codomain of the function? B. What is the range of the function? What is the range of the function? What is the range of the function? A, B, C. That is the full set B. No element has been kept vacant here. This works as the image of 1. This works as the image of 2. This works as the image for two elements, of course, in the domain. We don't bother. No element is kept vacant here. Therefore, to say or to notice that a function is 1, 2, we say that every element of the codomain works as the image for at least one element in the domain. And in very short tips to say B is equal to f of A. For this function also, we can see so many examples in our daily life. Suppose this is a computer lab comprised of only 3 computers A, B and C. In a particular college, there are only 4 students. These are to attend the practicals, in which there are only 3 systems. This person uses this system, this person uses this system, this person uses C. What about the 4th person? Can he be kept vacant? He should write the exams also. He should do the practicals also. So he must adjust with one of these 3 persons. That is, he should adjust with one of the 3 systems. He also likes to use the same system. There is no other go. So all these 4 persons will be adjusting with these 3 elements only to have images. That is a situation in which we can be in a position to demonstrate an onto function. This is the nature of an onto function. Therefore, to identify a particular person is onto function or a surjection, what should we have? B is equal to f of A. That is, codomain coincides with the range. Well, if A and B are finite, what can you say about n of A and n of B to define an onto function? Here, clearly, n of A must be greater than or equal to n of B. Greater than or equal to n of B. Why should it happen? We shall see what is there. Try to define an onto function here. 1 goes to x, 2 goes to y, 3 goes to z. This element is kept vacant here. It is not an onto function. It is not the character of an onto function. If at all it is an onto function, codomain must coincide with the range. What is the codomain here? X, y, z and t. But what is the range? X, y, z only. It is not an onto function. If you omit this element from the set, then it becomes an onto function. So what is the sin with this example? N of B is greater than n of A. That is why to define an onto function is a difficult task. Difficult? It is an impossible task to define an onto function here. Therefore, we must be having n of A greater than or equal to n of B to have an onto function, provided A and B are finite sets. All such explanations, discussions can be had when and only when A and B are finite. Just now we have seen 2 different functions, namely injections and surjections. That is, 1 functions and onto functions. If at all a particular function is both an injection and a surjection, then it is termed as a bisection. 2 types of jections. For the sake of fun, I am speaking like that. Surjection and injection. Those 2 things must happen in the case of a function for it being called a bisection. That is, a function which is both 1 and onto is termed as a bisection. You observe in the case of finite sets A, B, C, D, 1 to A, 2 to B, 3 to C, 4 to D. It is 1 because number of elements in the domain is 4, number of elements in the range is 4. It is onto because domain is equal to codomain is equal to range. It is both 1 and onto, hence it is termed as a bisection. Well, in the case of finite sets, if A and B are finite, To define a bisection, what must you observe? N of A is equal to N of B. N of A is equal to N of B. Of course, when A and B are finite. When A and B are finite. Even when A and B are infinite, it might be possible to define a bisection from A to B. It might be possible. We may come across so many such sets which are bisections even when A and B are infinite. In such a case, if there is a bisection between two infinite sets, then some others say that A and B are equivalent sets. Some others say that A and B are equivalent sets. Okay? Well, this is the nature of a bisection. By a bisection, we mean that function which is both 1, 1 and onto. Let us recall the examples of some bisections, famous bisections which we come across in our usual daily mathematical life. F from R to R defined by f of x is equal to ax plus b, a not equal to 0. No doubt it is a bisection. These are familiar examples. And then f from closed interval minus pi by 2 to pi by 2 to minus 1 to 1 defined by f of x is equal to sin x is a bisection. Similarly, f from closed interval 0 to pi to minus 1 to 1 defined by f of x is equal to cos x is again another bisection. F from R to R plus, what do you mean by R plus? Set of all positive reals defined by f of x is equal to e power x is a bisection. F from R plus to R, set of positive numbers to R defined by f of x is equal to log x, that is ln x, of course. These are the familiar bisections. You see, not only sin x and cos x, tan x, secant x, cosecant x, they can also be made bisections, of course, by restricting domain and range. Actually, for the function f of x equal to sin x, this is not the particular domain. For any real number, you can be having sin x. For any real number, you can define sin x. But to make that sin x a bisection, to make the function f of x equal to sin x a bisection, we have restricted that the domain must be like this and the range must be like this. In a similar fashion, we can observe for tan x, sin inverse x, cos inverse x, all the other trigonometric functions also. And those things will come under the heading domains and ranges of the function, of course. These are familiar bisections. Not only this, we can be having so many other functions also which we come across while solving numerical problems. Invertible functions and inverse of a function. What do you mean by invertibility? You observe here 1, 2, 3, A, B, C, F. From this diagram you say f of 1 is equal to A, f of 2 is equal to B, f of 3 is equal to C. And you draw this diagram, you trace the diagram in this way also. A goes to 1, B goes to 2, C goes to 3. You observe these two diagrams. One is mapped to A here, one goes to A, again A comes to 1 there. 2 goes to B, B comes to 2. 3 goes to C, C comes to 3. So just mutual interaction, rather making the reverse position of the images and pre-images. In this way, in this diagram we say that F inverse of A is 1. This function is termed as F inverse of A is 1, F inverse of B is 2 and F inverse of C is 3. Is it a function? Of course. Is it? Of course. This is a bisection, that is why that is also a function. One more thing, if it is not a bisection, what happens? Suppose element 4 is also there like this. Then F inverse of C, do you put 3 or 4? There has been a conflict there. One element should not have 2 images. F inverse need not be a function at all in that case. That is why to define an inverse, the original function must be a bisection. Original function must be a bisection. As you are able to define inverse, it is said to be invertible. It is said to be invertible. It is said to be invertible. And in general, if f of x is equal to y, then f inverse of y is equal to x, provided f inverse is possible to be defined. Yes, there has been a very good contact with the two words inverse of a function and composite function. So it is our necessary aspect to deal with composite function also at this juncture only. Later on again we shall discuss with the inverses and composite functions at a time. Now it is our aim to deal with the composite functions. What do you mean by a composite function? What does this diagram infer? There are two functions, one is f from a to b, another is from b to c. If you start at a, you will be able to reach c. Of course, you may be able to define a function from a to c also. How to name it? You have started from a and reached c, isn't it? Of course, at c, the function available is g. Could you reach g directly? No. Over f you have travelled. That is why this is named as g over f or g circle f. G over f or g circle f, and this is called the composite function of f and g. Therefore, to define g circle f, what are the things that you must observe? Domain of G and codomain of F must coincide. What is the domain of G? B. What is the codomain of F? B. In that case only it is possible to define G circle F. Forget about the diagram. There are two more functions, say H and psi. When do you believe that H circle psi can be defined? What are the things to be observed here? Domain of H and codomain of psi must coincide, unless or otherwise it is just not possible to define H circle psi. At times, in some examples, we see that both G circle F and F circle G are possible to be defined. What is that particular case? Look here. A to B. Function F is there. B to A again. Function G is there. Now, let us discuss F circle G and G circle F. Is it possible to define both? Let us see. Domain of F, A. Codomain of G, A. Excellent. It is possible to define F circle G. Again, domain of G, B. Codomain of F, B. Good. This is also possible to be defined. Therefore, you need not believe that always you are able to define both F circle G and G circle F. In particular cases only, it is possible to define both of them. In numerical problems, we shall generally come across real functions only, that is F from R to R, G from R to R. In such cases, we naturally and clearly observe that both F circle G and G circle F are defined. That is why problems like find G circle F of 1, F circle G of 2 in our earlier classes, say 10th standard and so on, like that. So, theoretically, for F circle G and G circle F, both of them to be defined, we must have the situation like this. One is from A to B, another is from B to A itself. In that case, we definitely define both F circle G and G circle F also. Well, we have noted what is the meaning of a composite function. And from earlier algebra, it is a very easy concept to find F circle G of X. What is F circle G of X? F of G of X. For every X in the domain of that function. Similarly, what is G circle F of X? It is of course G of F of X for all X belong to the domain of that particular function. And it is not a special case to discuss with and define that particular step. It's not necessary. Everybody is aware of that. F circle G of X is nothing but F of G of X, like that. Now, this is the right time for us to discuss with the relation, rather the utility of inverse of a function and composite function at a time. How can we use them? Let us see. Which is correct? F is a bisection is saying. So damn surely it is invertible. F inverse exists. Well, let us check. F circle F inverse. What is the domain of F? A. What is the codomain of F inverse? A. Is the function from A to A? Yes, this is correct. Don't leave the other options also. You discuss with them. What is the domain of F inverse? B. What is the codomain of F? F. What is the codomain of F? B. B to B. This is also correct. What do you say about this? What is the domain of F inverse? B. Because F is from A to B, F inverse is from B to A. Domain of F inverse? B. Codomain of F? B. So it is a function from B to B. If at all it arises, IB must come. He is writing IA, not correct. F circle F inverse is IB, he is saying. Is it right or not? Let us see. Domain of F? A. Codomain of F inverse? A. So it is a function from A to A. If at all the end arises, it must be IA, but he is writing IB. This is wrong. These two are correct. These two are correct. So without leaving any confusion, we must be able to decide like this. F circle F inverse and F inverse circle F, like that we define. What is the domain? What is the codomain? Like that you observe. Well, this is the way we link these two concepts, F circle G, composite function and an inverse function. There are so many functions that to be discussed, of course. Out of all of them, such functions which are frequently faced by us in numerical calculations and theoretical discussions, we shall look at them. Out of them, one even functions and odd functions. Even functions and odd functions. What are they? Even means, is it associated with an even number? No. It has a particular and peculiar definition. What is that? To define or to mean an even function, we must be having f of x is equal to f of minus x for all x in the domain. And in the case of an odd function, we must possess f of minus x is equal to minus f of x for all x in the domain. In the domain. This is the basic concept. You observe f of x is equal to, this is the definition, and these are the examples. F of x is equal to x square plus 1. F of minus x, x square plus 1. It is an even function. F of x is equal to x power 4 minus 2x square plus 5. Is it an even function? Of course, f of minus x is x power 4 minus 2x square plus 5. And then f of x is equal to cos x. Is it even or odd? What is f of minus x? Cos of minus x. What is cos of minus x? Cos x. So f of minus x is equal to f of x. It is also an even function. F of x is equal to mod x. What is f of minus x? Mod minus x. What is mod minus x? Mod x. Hence, it is also an even function. Well, let us look at some examples, some more examples for an odd function. In the case of an odd function, look at that. F of x is equal to x cube plus x. Is it odd? Of course. What is f of minus x? What is f of minus x? Minus x cube minus x is nothing but f of minus x is nothing but minus f of x. That is why it is an odd function. Well, I am writing f of x is equal to 5x power 7 plus 6. Is it an odd function? What is f of minus x? What is f of minus x here? This is 6 minus 5x power 7. Are you able to write this as minus f of x? No. This is not odd. Then, is it even? No, it is not even because f of minus x is not equal to f of x. So, in functions, if a function is not even, we need not say that it must be odd. If a function is not odd, you need not say that it must be even. There are so many functions which are neither even nor odd. Of course, in number system, we do not see such type of situation. If a particular integer is not even, you must say that it is odd. Similarly, if a particular integer is not odd, then it must be even. Such things do not occur in the case of functions. You observe this example. It is neither even nor odd. Yes. So, this is the basic definition of an even function. That is the basic definition of an odd function. Let us see some more examples for these two types of functions. F of x is equal to square root of 1 plus x square. The basic concept in the case of a function in which a polynomial is involved, even powers of x must only be present. Then only you say that it is an even function. Well, this is even. You observe this function. F of x is equal to e power 3x plus e power minus 3x. Is it even or odd? Let us observe. Calculate f of minus x. What is the things that is going to happen? E power minus 3x plus e power 3x. So it is nothing but f of x. Surely this is even. Why? Because f of minus x is equal to f of x. You see, without testing like this, we can be in a position to say directly that it is even with the help of, look here, if at all there is any function h of x which occurs in the form f of x plus f of minus x, if you come across any function like this, then h of x is even. H of x is even. This particular function looks like this. I write h of x, g of x equal to e power 3x. What is g of minus x? Like this. So, f of x, f of minus x. Let me give you one more example. G of x is equal to square root of 1 plus x cube plus square root of 1 minus x cube. Is it even or not? Is it even or not? Let us test. Let me call this f of x. What is f of minus x? This is. Therefore, this occurs in the shape of f of x plus f of minus x. No doubt we will be able to say that this is even. What is the basic thought that we must possess here? If at all any function occurs in the form f of x plus f of minus x, such function is even. Such function is even. Similarly, if at all you come across a function of the form f of x minus f of minus x, then this must be odd. This must be odd. Now, I change the sign here to minus. What is going to happen? It is an odd function. If I put minus here, what happens? That is an odd function. The basic thought is the function must be in the form f of x minus f of minus x. In order to notice that it is an even function, you must have f of x plus f of minus x. Like this, we can observe so many things related to even functions and odd functions.